Log on, tune in, find out. Another good idea from Cambridge.
Well, it's a great pleasure, an honour to be able to have a short conversation and some elaboration of your work with Neil Turok. Thank you very much, Neil, for making the time. When there might be all these emails waiting with other spam of a significant and interesting kind, which we'll come back to later. Anyway, tell me when and where you were born.
I was born in Johannesburg in South Africa in 1958, and I grew up in a family which was very political, always in trouble. Police used to knock on our door and come and raid my parents' book and record collection, looking for
They were short of records
materials. Yes. And so my parents were both very involved with the African National Congress and the resistance movement in South Africa. My father went to prison when I was 3 years old for 3.5 years, and my mother when I was about 5 for 6 months. And so I grew up in an exciting family environment. We left as refugees in 1966. We were allowed to leave South Africa, and we moved to Kenya and then Tanzania. Had a wonderful childhood in Africa. Got well and truly bitten by the African bug, and then we came to Britain.
You're skimming over in 2 minutes what usually takes me an hour, but so I'm just going to take it back.
Sure, no problem.
Tell me something about, do you remember your grandparents, for instance?
Yes, I remember my grandparents very well. When I was 5 years old, my mother went to prison for 6 months, and I went to stay with my grandmother, who lived in Durban. And she was a Christian Scientist. She believed very strongly in the gospel as preached by Mary Baker Eddy, and she took me to Sunday school, which I loved. I loved the Bible, I loved the stories, the ceremony of it all, and by the time I came home after 6 months, I was praying every night by the side of my bed, which my 2 older brothers found completely ridiculous. And after about a week, they'd broken me of the habit. So
You never look back.
I've never looked back in that way. But we used to have these funny debates about whether there was or wasn't a God. And one of the sort of clincher arguments, I think, when I was religious, my brothers said to me, okay, if there's a God, where is he? I said, oh, everyone knows that. God is everywhere. And so they said, okay, if he's everywhere, why didn't he shout out? I've just punched him. And so my answer was, well, he's very brave.
To which, and so it went on.
Yeah.
I mean, well, perhaps I won't go along this line, but you could argue that all your work is directed to the question of who he is and where he is and if he exists and so on. But
you could.
You could, but it wouldn't be true. I'll leave that to my philosopher friend here, Tina. But what was the occupation of your family, so to speak? Your parents were not only political, but did they do something other?
Yes, my father was trained as a land surveyor, and so he had a engineering/mathematical leaning. He taught me Pythagoras' theorem, for example, and how to make maps. I used to use his hand-cranked calculator to work out calculations to very large numbers of decimal places. And he interested me in the ancient Greeks because he was a keen student of philosophy. When he So he was imprisoned in 1966. Let me just get the dates right.
Because that's when you
No.
emigrated in '66. You said.
Yeah, no, we emigrated. He was imprisoned in '61, and for 3.5 years. And while in prison, he had a lot of time on his hands, and so he studied philosophy, took a degree by correspondence, and the philosophers he sort of fell in love with were the ancient Greeks. So he would often talk about them, and the pre-Socratic philosophers, essentially, people who had somehow suddenly seen the world with fresh eyes, had an incredibly clear perspective, uncluttered by tradition and mythology, and seemed to just really want to understand how the world worked. So he was a very strong influence on me, and his passion for politics, for freedom of black people in South Africa and for Africa generally was quite inspiring to me as a young person, and it still is.
What about your mother? What sort of person was she?
My mother was the carer of the family. She was left to look after 3 boys on her own when my father went to prison when I was 3 years old. And it was very difficult because she was a political activist herself, and so she was under constant harassment from the authorities. She was under house arrest some of the time. Her own family effectively disowned her because she had married my father, and they were very reluctant to support her, and they kept telling her she ought to leave him, and why wasn't she doing something sensible with her life, and so on. So she's an incredibly brave person, and she survived the 3.5 years with us, during which she was imprisoned herself for 6 months. And when my father finally got out of jail, she helped him to escape across the border of South Africa, and she then managed to get permission for her and ourselves to leave South Africa on condition that we never returned. And she brought us to Kenya, where we met up with our father again. So my mother really, if you like, was the backbone of the family. She continued to play that role. And all through our childhood, I think she was the one who supported us. And in many ways, my father was always busy with 100 schemes and ideas, and it needs someone to actually care for the kids and provide comfort, and not just how should I say, leading by example, which is how I think he behaved.
Schools. You went to school first in Kenya, did you? Or?
No, I was in school in South Africa. We left South Africa when I was 7, and so my first school was in South Africa. I was very precocious as far as I remember in school. I was extremely naughty, talked the whole time in class, but was moved up a year because I got very quickly bored with what we were being taught. So I'm sure I was an annoying child at school, always looking for ways around the system, and constantly breaking the rules.
At what age did you start to be really attracted to mathematics?
A very early age. In fact, it was more physics than mathematics. From the age of 3, I would play with water, pouring things, measuring things, weighing things. I loved geometry at that time. I was fascinated with nature. I collected insects. Remember very vividly when it hailed in South Africa, and collecting as much hail as I could in buckets. And
experimenting with it.
And experimenting with it. I loved experiments and chemistry, and animals.
When you went on to the next school, which was what, at 8 or 9?
At 7 we moved to Kenya, and I was there for 6 months in a school in Nairobi. I don't remember very much of that school. We weren't really there for long enough. What I do remember is that my father worked in the Ministry of Lands, or whatever it was called, the ministry which made maps. And I remember going to his work and seeing how they converted aerial photographs into topographical maps. And I found that just fascinating, that you could stare, you see it worked with these binoculars, that you could stare at 2 maps. So it gave you stereoscopic vision, and then you sort of scanned over the map and decided how high the land was, and that was used to finally produce the topographical map. So I found that very exciting and interesting.
I don't want to take too much of Tina's time, so I'm going faster than I might.
The real school is in Tanzania.
Ah, right.
That was the real school experience.
Tell me the real school experience then.
In Tanzania, I went to a fairly ordinary government school, but I had an absolutely exceptional teacher. She was a Scottish volunteer teacher who had an identical twin sister, and they're both teachers, and their mother was a teacher, and they all 3 lived together in the school. And so she was my maths and science teacher, Margaret.
Margaret what?
Margaret Carney.
That's K or?
C-A-R-N-I-E.
Yeah.
And in fact, I'm still in touch with her. I call her up every few months. She lives in Edinburgh now, and she's in her 80s, but she's an absolutely exceptional person. As a teacher, she basically taught me that I could do whatever I wanted to do. And so she gave me books, she sent me outside, she said, make a map of the school and a plan. And so I taught myself trigonometry, made measurements, made scale drawings of the school. Then she gave me books about physics. I learned Archimedes' principle, and pulleys and weights and forces. And we did a lot of projects. And really, she didn't instruct me. She simply pointed me in the right direction. And she was just so, convinced that I could do things, and so supportive, that gave me an incredible start. Subsequent to that, I moved to England and came to primary school in London.
At what age?
That was 10. At age 10 I came to Muswell.
So she was doing all this when you were about 8 and 9?
8 and 9.
Gosh.
So I came to London, and we lived in Crouch End in London. My father was selling Encyclopedia Britannica because he couldn't get another job. And I went to primary school in Crouch End, and they handed out these pages of calculations, long multiplication, division, addition, and I thought it was a joke. I thought, kids are actually doing this? I did that 4 years ago. Once you've learned the rules of how to multiply numbers, you don't need to do 100 examples. You know it, and you use it for real problems. You don't do it for its own sake. It just seemed utterly ridiculous. So I found the standard of schools in England, in spite of the fact we'd moved to England to go to better school, I found the standard way below what I'd had in Africa. Of course, the same wasn't true when I got to secondary school. Secondary schools in England were, of course, much better than they were in East Africa at that time. And I went to a very good school
Where was that?
in London. William Ellis. It was a grammar school. And
William Ellis.
William Ellis.
Yeah.
It was a grammar school in Highgate with some outstanding science teachers. You know, it has all the problems of grammar schools, I think. It's a kind of a grey environment, and there's certainly many things to criticise. Besides the fact, growing up in London, you know, is a lot less exciting than Africa. So it was a bit of a shock for us moving to England, the cold climate, the
Cold people.
darkness, the grey people.
Yeah.
But certainly the schooling I had was very good, and I have no complaints about it.
Were there any teachers there who
Yes, there
inspired you?
were. There were. I had a wonderful maths teacher who was a extremely modest but caring person. And even though I would say he wasn't by no means a show-off. I mean, it's a very common feature, I think, of mathematics. People, they love to show off. And teachers especially, show the kids how brilliant they are. He wasn't like that at all. He was actually very genuine and wanted you to learn, and he did love mathematics. He knew his own limitations, but he sort of made it clear to you that he hoped you could do more than he'd done with his mathematics. Very, very nice person. I remember some features of him, and for example, he at that time it wasn't the fashion to show your underpants above your trousers as it is now, but he did. You know, not deliberately. And so, you know, some of the kids found that rather funny. But he was a very sweet man.
Do you remember his name?
I don't remember his name, unfortunately. I probably could if I
Were you
tried.
ahead of your age group by that time?
Yes, I was. So I went to primary school in Crouch End, and I was they put me down a year, so I was in the correct age. But then I took the entrance exam to the grammar school, and they accepted me a year early. And thank goodness for that, because it would have bored me out of my skull to stay there for another year. So yes, I was always a year ahead.
Were there other things at school apart from you were now concentrating on physics and maths and things? Presumably?
Actually not. I was concentrating on biology. I loved nature, as I said. And so I collected beetles from when we were in Tanzania. I did that, and I was very serious about it. And I joined the British Entomological and Natural History Society, and in fact I was elected a committee member of the society when I was 13.
Gosh.
And I used to go every 2 weeks to South Audley Street in Kensington and meet with the amateur collectors who were almost all over 60. But they preserve this tradition, the sort of Victorian tradition of the animal collectors and classifiers, and they used to paint beautiful drawings of beetles and so on, and I loved all that. I loved the classification. I still believe that, you know, there's more beauty in a single beetle than there is in all of human works of art. And so there's no better way to appreciate nature than to see the incredible diversity and refinement of natural organisms. So I thought I was going to do biology, and because I loved mathematics as well, I thought I would do mathematical biology. And in fact that's what I came to Cambridge to do. But after I was here for 6 months or so and taken courses in theoretical physics, it really grabbed my attention, because it is the most powerful, simple effective part of science that we know of. You can write down an equation in one line, and that equation describes a million phenomena with incredible precision. And there's nothing really like that in biology. So I sort of switched over to physics as an undergraduate.
Perhaps you can explain something to me. I didn't even do O-level chemistry or physics, so I know nothing about it, but I've been looking at history of Cambridge University, and
Yes.
I cannot understand Dirac's equation. I can't see how you can write an equation which becomes a gold mine both for
Right.
other people and for yourself.
Right.
And it has properties which then illuminate things which you didn't have any idea of when you wrote it down.
Yes.
How is that work?
It's absolutely astonishing. But you see, Dirac, like everyone else, like Newton, Einstein, Maxwell, they were working on the basis of knowledge which had been previously discovered. Dirac wasn't working in a vacuum. He knew about relativity. He knew about Schrödinger and Schrödinger's equation. And he knew these things were correct because they had already proven themselves in various ways. And so Dirac said, well, I need an equation which satisfies both relativity and quantum theory as described by Schrödinger. And so he now had basically a mathematical puzzle to work out an equation which was consistent with relativity and quantum mechanics. And there is only one equation to write down, like the one he did. And so, he was just a lucky guy who happened to be in the right place at the right time, with the right mathematical tools. Dirac had an extraordinary mathematical mind. He had as far as I know, very little formal training in mathematics. He was trained as an engineer.
Like Faraday.
But, and he never liked mathematics for its own sake. He just invented it as he went along. But his equation now describes, of all the particles we know of in the world, his equation describes 90 of them, and the remaining 30 are described by, roughly speaking, by the theory invented by Maxwell and successor theories. But Dirac describes 3/4 of the known world. And it really is a single equation which can be taught in 2 or 3 lectures.
One day I'll come to your lecture. But this is moving on to Tina's work. So let's just finish off on the autobiographical. You came to Cambridge. Was there anyone at Cambridge who taught you or lectured to you who really influenced you at that time?
Yes, I think there was one thing which influenced me very strongly coming to Cambridge, and which I appreciated, which is that the course was completely unsystematic. The first lecture course we took was called Modern Physics, and it was lectured by Tony Hewish.
Oh, yes.
And it involved hand-waving, quantum theory, radio astronomy, a little bit of relativity.
The hand-waving is Hewish hand-waving.
Hewish hand-waving.
Yeah.
A little bit about data and how you make sense of it. No mathematical derivation in the course was more than 2 or 3 lines, but it gave you a glimpse of a lot of exciting science and ideas and so on. And that was really very deeply influential. And I think it was a model of its time. Mostly when physics is taught at universities now, and certainly in the US, in the strongest physics universities in the US, it's taught in a very systematic way, where it takes you at least 2 years before you get to anything modern. And I think that's a real big mistake, because you want to grab people as early as possible. Once they're motivated, they'll learn much faster than if they simply see that they have to plough through 2 years. So I think without that course I may not have gone into physics at all.
Interesting.
Yeah.
then at the end of it, we're skipping very fast, but the end of that, did you go on at Cambridge to start a PhD, or what?
Yes, when I finished at Cambridge, I'd done very well here and had a scholarship and so on, but I was tired of it. There were things about Cambridge I didn't like. It is an elitist institution, and I'm not against that if it's elitism, if it's intellectual elitism in the best sense. In other words, if people are really interested in ideas and discussion and innovation and so on. But I'm afraid at Cambridge a lot of the elitism ends up about having formal dinners, students who come from perhaps middle class or lower middle class backgrounds end up wanting to pretend that they are, almost aristocrats, and it becomes basically farcical. And so I didn't like that.
Which college were you at?
Well, I was at Churchill College, which is a science college.
Was Cockcroft then?
Pardon?
Was Cockcroft
Cockcroft and then Tizard.
Yes.
Tizard. So I liked the college, I liked the tutors and so on, but I didn't like to see the students getting more and more interested in sort of putting on airs and graces, I would say, which didn't, I just didn't fit in with. And so I decided not to stay here to do part 3 mathematics, which was the standard thing to do for a Cambridge person. So instead I went to Imperial College and I took their masters in theoretical physics and then a PhD. And that was very interesting. It was very difficult. Life in London is nowhere near as nice for a student as life in Cambridge is. And so that was quite a lonely time to go to a place like Imperial in the middle of London, tiny student digs, all the students go home in the evening, so there's no real college life. And plus you're working on a PhD, which in theoretical physics mostly consists of banging your head against a wall. And you have no idea whether you have any talent, whether the problem you're working on makes any sense, whether there's any future in this. And so I spent 2 years like that in London without a clear idea of what I was doing. In fact, the first year I spent, I worked extremely hard on the problem which I discovered after 1 year was not an interesting problem. But you learn through this process. But it's not an easy route, and I would advise anyone thinking about pursuing theoretical physics to be very careful that you are really willing to put up with some very hard times. It's not a subject where you get a quick reward. Mostly it's extremely frustrating and difficult. So
what did your parents were in London, weren't they? But you didn't live with them, you lived in digs.
No, I lived in digs. My father worked for the Open University. And he was very, work-centred, I would say, very committed to his work. I used to see them regularly, used to come home for weekends. My mother would cook a nice meal for me. They lived in Watford. Yes, after I'd been there in fact, while I was in Cambridge, they moved to Zambia. So they essentially weren't around for long periods.
And then after that, after the PhD,
After PhD, I went to Santa Barbara. I was lucky enough to find a mistake in the paper by a very famous scientist who later won the Nobel Prize.
Who was this?
It's Frank Wilczek. So I found a mistake when I was a graduate student, and he came to visit Imperial, or I saw him at a conference. He came to England for a conference, and I saw him, and he graciously accepted and withdrew the paper. And so I wrote a paper with my advisor on that problem. And then I got a postdoc at the Institute of Theoretical Physics in Santa Barbara, which is probably the leading such institute in the world. Fantastic place, interdisciplinary. I think they had 3 permanent faculty when I went there, and about 25 postdocs. So basically we didn't interact with the faculty very much. They more set the tone and the quality, but it was just left to us to find other postdocs to work with. And as a result, I worked in many different fields, and sort of looked around to find a niche for myself, which was good. There are actually very few places like that today, and even that institute today has a academic staff of more like 10 or 12, and far fewer postdocs. So the balance has sort of shifted. But what was very nice about it was a new institute, and just with a sort of very freewheeling atmosphere. And they said, all we're going to do is to try to gather the brightest postdocs in physics from around the world, and we'll see what they do. And that's what you should do. And every single one of those postdocs I was with in Santa Barbara now has an excellent position in theoretical physics. I mean, it's astonishing, the success rate. And yet there was no planned mentoring or supervision of the postdocs. It was interesting.
I was thinking maybe this is the point where we could turn over to Tina, because we're just getting on the edge of your work and life and so on. Is that okay with you?
That's okay with me. That's fine with you.
Okay. So I'll sit like this, and you just talk to Tina. This will be fine.
By the way, this teacher that I mentioned, I lost contact with her after Tanzania. And then I came to Cambridge in 90...
this is the one in Edinburgh?
The one in Edinburgh. So I lost contact with her after the age of 10, when we left Tanzania. And then I came to Cambridge, and I appeared on a couple of years after being here. I did some work with Stephen Hawking, and I was on a TV documentary program, which she saw. And so she wrote me a letter, and she said, "Are you the same Neil Turok who I knew when you were 10 years old?" And of course I was just jumping up and down. I couldn't believe that I'd found her again. I went to see her in Edinburgh, and she was the same person she always was. So I've stayed in touch with her ever since.
I was wondering how that happened. I mean, that happened with my history teacher, who I lost contact with for 25 years, and then I wrote a book, and he wrote to me saying, I enjoyed your book, and I've kept in touch. I see him a lot. And I still have the same mixture of reverence and terror of him. I mean, I send him everything I write, and I really pay attention to his comments.
Well, she had a very perceptive comment when this is the age of 80. I went to see her in Edinburgh, and she's by no means sophisticated scientifically. I mean, she taught primary school maths and science. But I started to tell her what I worked on. And she sort of interrupted me. She says, "Look," she says, "I'm not going to, this is not really what interests me." She said, "There's only one important question. And I've asked it to every speaker I've ever seen talking about cosmology or astronomy. And the question is, what banged?" Okay. You keep talking about the Big Bang and a strong Scottish accent. What banged? And I thought, yeah, that's a good question. So coincidentally, it was what I was working on, but I've subsequently used that as the title of talks that I give, and it was attributed to her. And indeed, it is the most important question.
What banged? Lovely. Okay, so Tina.
So maybe we can start with this most important question: what banked?
Yes.
My questions will mainly use the material that you present in your book, Endless Universe. And maybe to begin with, if you can just summarize very briefly what the cyclic model hypothesis is about.
So the original motivation for the cyclic hypothesis or cyclic universe picture came from a theory called string theory and a development of it called M theory. Now these are our best current attempts to unify all the laws of physics into a single mathematical framework which is consistent both mathematically and logically, and also consistent with everything we know about the world. And so a lot of progress has been made in string theory. There does seem to be a single mathematical framework within which all the laws of physics fit. So Einstein's theory of gravity, Maxwell's theory of electromagnetism, Dirac's theory of particles, these all fit together in a single framework, now called M theory. And other people had developed this. I wasn't responsible for this at all. But to me, the application of M theory, and in fact the test of it, the true test of the theory, would be to see whether it could describe cosmology, could it describe the universe. So we developed so in fact the origin of the cyclic picture goes back to a workshop in '99, where we invited the leading researchers working on M theory and leading cosmologists together just to see if anything interesting could come out.
This was in Cambridge, at the
In
Newton
Cambridge,
Institute.
at the Isaac Newton Institute. And we had several lectures, and during one of these lectures, me and Paul Steinhardt, who's my long-time collaborator from Princeton, but we'd never worked together at that point. We both had the same idea that, and it's a very simple and physical idea, that within M theory there are these objects called branes. And brain is shorthand for membrane. But you can have a one-dimensional brain, which is a string, or a two-dimensional brain, which is a membrane or a surface, like a soap bubble. A three-dimensional brain, which is space, three-dimensional space we live in, or four-dimensional brain, and so on, up to 10 dimensions. So theory says that brains of up to 10 dimensions can exist. And the world, if we want to picture it that way, consists of a 10-dimensional brain with other brains of lower dimensions embedded inside it. And the intriguing thing is that you can't do this in an arbitrary way. That once you've decided you want a theory of 10 dimensions, you have to have all the other brains of different dimensions within it, and the rules whereby they interact are unique. So there's no adjustment possible in the theory, so that makes it very attractive. But up until our workshop, nobody had seriously tried to apply this to cosmology. At our workshop, we were fascinated with the particular picture which had emerged, that the way to get from 10-dimensional M theory to the real world was to get rid of 7 of the dimensions by curling 6 of them up in a little ball. So at every point of this room, you should really imagine that if I only had a microscope, a really powerful one, I could look very closely at each point of space, and I would actually see an extra little ball of 6 dimensions. It's a bit like a carpet, where if I look at a distance, I just see the floor, but if a surface, but if I look closer, I'll see a weave in the carpet itself. So every point of 3 dimensions will be another 6 curled up. And I'll come back to that, because that's, even though it's at first sounds shocking, and it sort of sounds like you're hiding a multitude of sins in these unobserved
Brushing under the carpet, so to speak.
Pushing them into the carpet, indeed. It's a very beautiful idea when you look at it more closely. But most intriguing to us was that there was a seventh dimension, which was even more bizarre. The seventh dimension is a gap, and it's a gap between two objects, which are three-dimensional brains. And these, so you have a picture of the world that there is a three-dimensional brain we live in, our world, and our particles we're made of travel around on this brain. Light travels in this brain. But just next door to it, there's another brain. And these two brains are called end-of-the-world brains, meaning that they're the end of the seventh dimension. That there is nothing beyond them, they're almost like mirrors. And so the world really is the sandwich with nothing outside it of the seventh dimension of space, in between the two three-dimensional brains we live in, and in every point of those three-dimensional brains there's another 6 dimensions curled up. So our thought was, what happens if these two three-dimensional brains collide? What does that look like? Must be a pretty violent event, because the whole seventh dimension disappears for a moment. But on the other hand, the three-dimensional brains we live on do not shrink to a point when they collide. They simply move together. And therefore, it can't be like the Big Bang, because as we knew, the Big Bang is an event where all of space was at a point. That's the conventional picture of the Big Bang that came out of Einstein's theory. And so we could see immediately that here was another possibility for a bang, which is that the space we live in did not shrink to a point. All that happened is a collision between another world and ours. And when we worked through, so subsequent to that, we worked through the mathematics of this, and we discovered that this event of the brain collisions indeed appears, if you try to describe the setup using Einstein's theory of gravity, it appears just like the Big Bang. It is the Big Bang, for all intents and purposes, just that in Einstein's theory, there is not a complete description of these brains colliding. And when you add that element in, you find that indeed space does not shrink to a point at the back. Space is extended. And so now you have the possibility of a physical mechanism which caused the Big Bang, which is describable. See, if the whole universe came out of a point, that would not be mathematically describable. I mean, a single point, we don't know how to describe its structure or anything interesting happening. What we use in physics is always, they're called differential equations. We difference neighboring points. If you've only got one point, you can't write a differential equation down, and so you're lost from the beginning. But if you had a picture of the Big Bang that, no, in fact it was an extended bang across space, now you have the possibility of describing a physical mechanism which can cause the bang. And that's really where the cyclic picture emerged. So we were trying to understand how to describe the Big Bang singularity. What we realized is it could be the collision between two of these brains. And that meant there was time before the Big Bang. But of course, if these two brains can collide once, then they can collide again. And quite quickly, after we'd invented the initial model, called the ekpyrotic model. Ekpyrotic means out of fire. And the ancient Greeks had this picture of cosmology, that somehow the universe began in a conflagration. And so this was we call this picture of the colliding brains an ekpyrotic model, in homage to the Greeks. And then when we realized it could happen many times, and maybe indefinitely many times, we called it the cyclic model. Mm-hmm. That was a bit long, I'm afraid.
No, that was wonderful. This fourth dimension is
Yes.
really intriguing.
Yes.
While reading about Cyclic Universe, many readers that might read about it unattentively would have thought about it as a breathing universe,
Yes.
like expanding.
Yes,
And
that's right.
but you say that the three dimensions
Yes.
expand constantly.
That's
so the
right.
only thing that shrinks
That's
is
right.
that spring-like force
Exactly.
between the brains in the fourth dimension.
That's
And
right. It's essentially like a pump. I mean, this is pumping
Mhm.
in this direction, but the universe is expanding in the other directions.
And this gap is really small. It's 10 on minus 30.
Yes, 10 to minus 30 meters. Yeah.
Mhm. But is it possible to imagine where it is? Well, it is in this fourth dimension. You
Yes.
said it's in the end of
Yes.
the world. So would
Yes.
it be possible? How can we imagine where this is? Is it like
Yes.
everywhere, or is
Yes,
it?
it's everywhere. So every point of our three-dimensional world is just 10 to the minus 30 meters away from a corresponding point in the neighboring world, which is the, if you like, the mirror world, sitting at the other end of the seventh dimension. So we're only just separated from it by absolutely an immeasurably small distance. And it's interesting to ask, are there any other manifestations of this extra dimension? In fact, the origin of this seventh dimension and the way it was first understood was that in our world there's a peculiar asymmetry in nature. Left-handed objects are not the same as right-handed. When you have neutrinos, a certain kind of elementary particle that's a very tiny mass, neutrinos only come left-handed. The only ones we've ever observed in experiments are left-handed. There are no right. Left-handed means that if it's traveling along in the direction of your thumb, its spin goes in the direction of your fingers. So it spins like this. There are no right-handed neutrinos. Anti-neutrinos are right-handed, but neutrinos are left-handed. And that's always been a puzzle. Why is nature asymmetrical? Well, within the reason this was invented, this two-brain picture was invented, is precisely so that the left-handed guys can be on our brain and the right-handed on the other brain. And then mathematically it all works out.
Wonderful. But you said atoms and light and those things exist just inside one brain and then in the
Yes.
other also.
And the other brain, there's other stuff.
Yes, but
Right.
there is one thing that connects them, and that is the force of gravity.
Exactly.
And how does that look like? You mentioned that it might be the dark matter is the gravity of this other brain.
The dark matter might be the matter on the other brain.
Mm-hmm.
The matter on the two brains interacts only through gravity. So the dark matter would be on the other brain, we'd be on this brain, and gravity would run across the gap. So the way we understand gravity is that gravity is really the curving of space. That's what Einstein understood, is space is not a rigid substance, it can bend, and the bending of space is precisely the force of gravity. So the sun bends space, and that's what keeps the planets going around in circles around the sun. And in this M-theory picture, it's really what I call Einstein plus plus. You know, in computer languages, there are various languages like C, and then there's C plus and C plus plus. Well, M-theory is just Einstein plus plus, because it says that there's not just the 3 dimensions, there are actually 10. Then there are all these other objects of different dimension, but each of them behaves exactly in the manner Einstein envisaged. So they're all flexible objects, they can deform in various ways, and that is gravity. So you have these two brains here. Matter moving on this brain deforms the space in between the brains, and that's how gravity is transmitted across the gap to the other. And that's how the dark matter influences us.
Mm-hmm.
So this is kind of a neat picture, because it does naturally give dark matter, predicts there should be dark matter, and it predicts that dark matter should be visible only through gravity. And that's exactly what we see. You know, we see a galaxy with stars running around. There seems to be some dark matter there, but we can't see the dark matter with light because it doesn't interact with light. Light only moves on our brain. The unfortunate thing about this picture, if it's true, is that it's really hard to test, because since our only way of interacting with the dark matter is through gravity, we can't make dark matter in the laboratory. That's just way beyond current, the energies we can get in current laboratories. So, in a sense, it's an unpleasant situation. I mean, you have this marvelous theory, but we don't yet know how to test it. And so all the more reason for, I believe, that we should focus on the Big Bang, because we know the Big Bang happened, we can measure the outcome of the Big Bang in many ways, and we can use that in order to check whether this theory is right.
Mm-hmm. How can we check it? How can that be checked? You mentioned
Yes.
gravitational waves in your book.
Yes, I mean there's surprisingly a remarkably direct way of checking this picture that the Big Bang was a brain collision.
Mm-hmm.
And that's using gravitational waves. So the gravitational waves are ripples in space which travel at the speed of light. We have never detected them directly because they interact very weakly with matter. And so even though we believe the universe is full of them, we haven't been able to measure them yet. They will be measured within the next 10 years. There are a lot of experiments now, very precise experiments, which are going for gravitational waves, and we're 100% sure they will be measured in the next 10 years. When they are, this will be a new window on the universe, because we will see black holes colliding, all kinds of violent phenomena which emit gravitational waves. We'll just be able to see them directly. Because gravitational waves interact so weakly with matter, that's a wonderful thing from the point of view of seeing the Big Bang, because it's just like the universe is transparent to gravitational waves. So when we look out at the sky now, we see the radiation from the Big Bang, the microwave radiation. And that shows us the universe as it was 13.7 billion years ago, but about 300,000 years after the Bang. Because only then had the universe become transparent to light. Before that time it was very dense, very hot, plasma, which is opaque to light. So using light we can never look back to earlier than 300,000 years after the Bang. But gravitational waves take us right back to the Bang itself. So these waves emitted at the Bang would just travel straight through the plasma without any interference, and straight into our detectors. And so currently there are experiments being planned. There's something called LISA, the Large Interferometric Space Antenna, which is a set of 3 satellites which will be put in space in 2013 or so. And they will be looking for gravitational waves coming out of the early universe. Now, the way in which you check this theory of the brain collisions, first of all, is a negative check. So we have to discuss a little bit the alternative theory.
Yes.
So the standard picture of the Big Bang just accepts that the universe emerged from a point without any explanation. Just says, well, that's something we can't describe. Let's just assume the universe sprang into existence okay, at some point in time. What state would it have had to be in order to end up like it is today? And the answer to that question is initially very, very puzzling. Because if you have a tiny universe springing into existence, how did it get so big and smooth and uniform in all directions as we see it today? And that was just seen as a paradox for a long time. In particular, you can say, if I look in this direction on the sky, I see a certain temperature of the microwave radiation, a certain number of galaxies, and so on. Look in the opposite direction. You see roughly the same thing. How do they know about each other at the Bang? 14 billion years ago, because the light from them is only just, reaching me. So they certainly can't have known about each other. There's no way to communicate. So puzzles like this led to what's called the standard picture of cosmology. And according to the standard picture, you simply assume the universe jumped into existence, and you assume that it was full of something called inflationary energy. And inflationary energy has the strange property that it makes space expand exponentially. You can do this, you can add this energy into Einstein's theory of gravity, and it's a sort of repulsive form of energy which blows the universe up, makes it very smooth and uniform in all directions. But it's never really explained why the universe started out that way. So that's the standard point of view. Now, to come to gravitational waves, this epoch of inflation has a very dramatic side effect, which is when you make the universe blow up exponentially, it's such a violent process that you generate lots of waves. It's almost like hitting a bell or an explosion of some sort. The ripples in space-time, which are just there, present in the vacuum, even in empty space. When the universe starts to blow up exponentially, and it blows up by a huge factor, e to the 10 to the 100, is what typically happens in this inflationary theory. This enormous blow-up spews out gravitational waves. It takes these quantum vibrations in the vacuum, turns them into real big long wavelength vibrations of space. And we should be able to measure those. So that's what inflation predicts gravitational waves. The cyclic model is much gentler. You have these two objects, they drift together over periods of billions or even longer, trillions of years before they collide. When they collide, all of space isn't at a point. It's all spread out. It's simply that this collision has filled space with radiation. And then it subsequently expands. So it's a much gentler process, and you don't get the gravitational waves that you would get with inflation. So if these gravitational waves are seen, they will instantly disprove our model. So it makes it testable and exciting. Next year, so even though the direct detection of gravitational waves will only be possible in about 2013, there may still be a detection before then. Next year, something called the Planck satellites will fly, and they have a means of detecting gravitational waves indirectly through their effect on the microwave radiation coming from the early universe. So Stephen Hawking bet me, when we first came up with our model, I gave a talk about it here in Cambridge, and Stephen always likes a bet, and so he said, I bet you the gravitational waves will be detected by Planck, and your model will be proved wrong. And so I said, I'll accept your bet for any amount of money you care to name, at even odds. And so far he's refused to name an amount of money because he doesn't want to bankrupt me. But he has promised me that we will decide on something for the bet. The other idea I had is that he plans to go into space in, I think, 3 or 4 years from now. Richard Branson has offered to take him in space on Virgin Galactic, and so I said, well, let's say that if I'm right, I go into space. But he didn't accept that one. So we are living on the edge. It could be that next year our model will be dead, and to me that's exciting. I have worked on theories before which have been proven wrong. And even though it's disappointing and, you prefer them to be proven right, I think it's good science. And I think, one should be humble in the face of the universe. The best we can do is try to make the most complete and consistent models that we can. and then we have to test them as ruthlessly as we can in order to prove them wrong. And if they are proved wrong, we should say, yes, that's progress. I mean, at least we now know, that avenue is ruled out.
Mm-hmm.
So I'm perfectly willing to. In fact, I'm only really interested in theories which can be proven wrong. I would say it that way.
So to proceed with cyclic model,
Yeah.
one of the protagonists of cyclic model is the dark energy.
Yes.
What is this enigmatic thing, and what role does it play in the cyclic model hypothesis?
So dark energy, from the modern point of view, is nothing but the tension of these brains. So as we're all used to, if we have a surface like a rubber sheet, it has some tension, and so it has some resistance to being deformed. And when Einstein first developed theory of general relativity, he realized that space, ordinary three-dimensional space, could in fact have such a tension. It was perfectly allowed by his theory, and he called that the cosmological constant. Reason it was cosmological was that this tension has a very peculiar effect when you combine it with gravity. So we're normally used to thinking of the tension as causing something to shrink. But in fact, when you put a tension into Einstein's equations, and if the whole of space is full of this tension, it does the opposite. It causes the world to expand. And Einstein used this to make a static universe model. So what he did is he assumed the world was a sphere, three-dimensional sphere, and then the gravity of ordinary matter would make it tend to collapse, because matter attracts itself under gravity. This tension would cause it to expand, and he balanced these two forces against each other to have a static universe. Unfortunately, it was unstable, so if it happened to shrink a little, it would collapse. If it happened to grow a little, it would blow up, and his model didn't make much sense. So he quickly abandoned it. And then, of course, he regretted having made this model, because 10 years later, it was found the universe is expanding, and he should have just predicted that. The universe can't stand still, it has to expand or collapse. But so he then abandoned this cosmological constant. But we always knew it could be there, and in fact the surprise is, or has always been, why is it not bigger than it is? Why is the tension of space not huge? There seemed to be nothing in the laws of physics to prevent that. And there are all kinds of contributions to the tension. You see, even if you have space with no tension, and you start adding particles and fields to the universe, each one of those particles contributes something to the tension. And to end up with very small tension is really difficult. You have to somehow cancel the contributions from different particles. It's always been a huge puzzle why the tension is so low. Then in the late 1990s, quite strong evidence emerged that the tension is not zero. It's actually positive, and that we call the dark energy. It's nothing but another name for the same thing. So it appears that apparently empty space, just the space between ourselves and other galaxies, is actually full of energy. It's the energy associated with the tension of three-dimensional space. And as I say, from the modern point of view, this is entirely what you expect for a brain. If space is a brain, it has a tension. So the surprise is that it's so tiny. Why is it so tiny? Now, if you try to quantify how tiny is it, it turns out that it is 10 to the power minus 120. So that's 10 to the 120 zeros followed by a 1. Point, 10 to the 120 zeros and a 1. And so it's ridiculously tiny in the natural scale determined by gravity. But nevertheless, it's important enough that it matters in the universe today, otherwise we wouldn't have seen it. So it's very important for the future of the universe, because it causes it to expand faster. So whereas matter makes the universe slow down its expansion, this stuff speeds it up. So if we now follow, so we're currently 13.7 billion years old, if we follow another 13.7 billion years in the future, this stuff will really have taken hold, and it will have begun to dilute away the galaxies exponentially. And we need to wait a few more tens of billions of years, all the galaxies we see now, almost all of them, will disappear from view. They're just diluted away. We'll actually just see them go redder and redder as they're accelerated away from us, and they'll disappear. So we will be alone in an empty universe, surrounded perhaps by our nearest neighbor galaxies, but nothing else. And so people in the future, or scientists in the future, will be very puzzled by the universe. They'll find themselves in an apparently empty universe. They won't see the radiation left over from a Big Bang, because it will have been diluted away, and it will look very different than our universe today. So, faced with this situation of a universe which started from a Big Bang, which was indescribable, which ended up dominated by dark energy, which is mysterious, we thought we would try to see things from a different point of view, and that's how the cyclic model arose. So we had this picture that the bang could be a collision between brains, the brains would separate, and possibly they would come back and collide again. Now the question is, how does dark energy fit into that picture? And what we discovered was something rather simple, which is that when the brains separate, if they do have some dark energy, that causes them to expand in this dimension and stretch out and become very flat and very parallel to each other. And then this dark energy can actually decay. In fact, the dark energy can be the source of the force which brings them together. And as the dark energy decays, they will run together and collide again and make another Big Bang. And so what the dark energy does is it makes the universe empty, smooth, vacuous, and ready for another Big Bang, which will produce another universe, which is very big and very smooth, will be emptied out again by the dark energy. So in fact, the dark energy is like a stabilizer. If you didn't have any dark energy, these brains would collide, their wrinkles and deformations they acquired in one cycle of evolution would be magnified the next time, and the whole universe would become more and more contorted and violent and disorganized. The dark energy keeps it all organized, and basically also provides the power which ends up causing the brains to collide and smooths them out afterwards. So it performs many functions within the model. Without dark energy, our model doesn't work. So whereas in the conventional picture of cosmology, dark energy is not necessary, it's just an afterthought. It's something we have to add to fit the data. It doesn't play any kind of determining role in the model. In our model, the whole model doesn't work without dark energy. So that's interesting. And then finally there's this big puzzle, why is it so small? Now I would say people working in the conventional framework have given up trying to answer this question. They say we will never explain why at the Big Bang, whatever produced the bang somehow made the choice, I'm going to fill the universe with radiation, matter at huge densities and energies, and then I'll just add in 10 to the minus 120 of dark energy. Okay, no one will ever understand that. Why did they do that? Why did the physics determine this value for the dark energy? So they've basically given up explaining it, and instead they resort to something called the anthropic principle. Anthropic principle says maybe all kinds of universes emerge or are created, but we're not there in most of them. And so if the dark energy was much greater in magnitude, it would have killed us, or our ancestors, and so we wouldn't be here. This is a kind of appealing argument in some ways, but when you look more closely, it doesn't actually have any predictive power at all. It's more a rationalization. It's more saying, well, this problem is really one which we'll never understand. So I don't find that explanation appealing. In our case, if you have this picture of a very old universe, much older than 13.7 billion years, in previous epochs, the dark energy played a huge and even controlling influence. Then you have a huge amount of time for this dark energy to relax. If its values can change, and in these theories like M theory, everything can change. All the laws of physics are actually dynamical. All the parameters can change. Then this dark energy can change over very long periods of time. And maybe what's happened is the dark energy has settled down to a value which is just right to keep the universe cycling in a stable fashion. So it's as if you have an engine or a motor, and you have a source of fuel, and you switch it on, and initially there's some transient period, but it settles down at some value. And given that the universe is able to have long cycles, it's entirely conceivable that dark energy has settled. So we've published some papers on this idea, and it's a radical alternative to the standard view. But I think what we have shown is that technically we can construct mechanisms which, again, it's a sort of technical use of the word natural. We use it to mean when we don't have to dial parameters to ridiculous small values. We can make a model which will self-adjust the cosmological constant down to the small values like the ones we see today. It's only a model. It's not clearly true. But I think what the dark energy has done is made us really rethink our concept of cosmology and the Big Bang. Whereas people had seen the Big Bang as somehow, a one-off intervention which made a universe with everything we see. Now that picture doesn't seem to be coherent. Why would the universe work out the way it has? If it was produced that way.
You also write that no form of energy in the past or the future ever goes out of existence, and that when cosmologists study dark energy today, they are also studying the same type of energy that dominating during intervals in the distant past, and that will dominate in the intervals in the far future.
That's right.
Could there be any information stored in the dark energy somehow about the past and the future of the universe?
Yes, definitely. So in this cyclic model, as the universe passes through one of these violent events, where it goes from being empty and full of dark energy, empty of matter but full of dark energy, it goes to being full of matter and radiation. What happens is that any signals or radio waves left over in the previous cycle do make it through. I mean, they will be there. You will need very, very sensitive detectors to read it. But in principle, it's all there. Nothing is ever lost, and so that's an exciting thought, that actually we could possibly communicate our discoveries about science to the future, and future generations who live in future cycles could one day receive it. What actually happens near one of these events is that all the particles we're made of, as the brains collide, they lose their mass, which is to say they become massless, and they all move at the speed of light. So the only entities in the world which are present at the bang itself are moving at the speed of light. And so it would be a very unfamiliar world, where all our particles, we would be sort of, we'd literally fall apart in a burst of radiation. And then immediately after the bang, we would be reconstituted into material objects. So it would be a very dramatic and violent event, but there's nothing to stop radiation going through the bang.
There is another interesting thing in your theory, and this is a big crunch.
Yes.
Is this big crunch just another name for the Big Bang? Are those
Yes.
the same things?
Same thing. Exactly. It's a collision between these two brains.
So maybe something more about the extra dimensions.
So, according to our current understanding of the laws of fundamental physics and our best unified theories, the laws of physics we see in 3 dimensions are largely determined by the size and shape of the extra dimensions. So at every point in this room there's another 6 dimensions of space curled up in a little ball, a rather complicated little ball. It may have holes and brains are wrapped around it and so on, but a rather complicated configuration which we can study. We know mathematically how to study. And the detailed configuration of the extra dimensions actually fixes the physical laws we see. So electromagnetism, the strong force, the weak force, the different spectrum of particles we see, that is fixed by the configuration of the extra dimensions. So at one level, we haven't solved these problems in physics. We haven't said, yes, I know why there are 3 colors of quarks, or why electrons come with neutrinos, or we haven't really understood those problems. We've just converted it to another problem, which is, why are the extra dimensions the way they are? But that's progress, because you've taken an apparently insoluble problem and you've converted it into another problem, which may or may not be solvable. But from my point of view, what makes it interesting is that we've learned from this framework that not only do the laws of physics govern the universe, there are simple general laws governing the universe, but the universe governs the laws. In other words, the configuration of the universe determines what the laws are which govern the universe. So it's all very self-referential. And more to the point, if we understand cosmology, see, cosmology is the study of the structure of the universe. Well, we better include those 6 other dimensions. And if we understand their structure and why they assumed the structure they did, then actually we've understood all of physics. So all of physics is determined by the structure of the universe. Then you say, well, where did all that come from? When was this structure determined? What physical processes? Well, of course, it came out of the bang. And so when this bang happens, you should not only study the gap between the brains, which cause them to collide, but the other 6 dimensions are doing something in this process at the same time. And it better be mathematically consistent. And maybe it involves changes in their configuration. They can change. And once you've understood the whole process of the Big Bang, maybe you will understand why the universe emerged not only with the structure it has, but also with the structure of the extra dimensions it has. And then you actually have understood all of physics.
Mm-hmm.
So the interesting thing is how all these questions have in fact become one question.
Mm-hmm.
And the question is, what banged?
Mm-hmm. And do you think we will ever find a final true answer to this question, and that you think that universe is actually a cosmos that can be explained rather than a chaos that cannot be explained according to...
I don't know. I don't know if there are limits to knowledge. Some people, I think in the last few years, have become rather pessimistic, and they have resorted to this anthropic principle or other similar arguments to say, you know, this is the end of the road for physics. Essentially, some people do argue that. I don't know. But I know that if we take that attitude, we'll get nowhere.
But you do state in the book that this is the best time for a cosmologist of all times, and that you are very thankful that you live at this exact moment. Why? Because
the last 10 years have seen unimaginable amounts of data collected from the universe. I mean, I was a cosmologist in '92, before the COBE satellite mapped the universe for the first time. And at that time I was seriously considering giving up, because there was most of the discussion was based on prejudice, or there wasn't any good data. And so you had schools of thought, and some people were making galaxies this way and other people that way, and there wasn't any clear-cut data to discriminate between the theories. 92, the satellite went up and mapped the universe, and suddenly gave us a clean picture of the Big Bang. It was just phenomenal. And ever since then, the last 10 years, we've had this stream of high-quality data, and we now have the prospect of measurements of gravitational waves looking right back to the Bang. It's a unique period in human history where not only are we speculating about the origin of the world, but we actually have the data to test these theories. So I think to be pessimistic now is really ridiculous. I mean, people have been waiting for at least 2 millennia to answer these questions, and probably hundreds of millennia to answer these questions. We have the data. You want to give up now? You must be mad.
When the idea was born, you wanted to discuss it right away, but that particular night you were going to see a play Copenhagen in London, I read. And what made me thought of one thing, because the play Copenhagen is discussing ethical problems of science, of Bohr and Heisenberg. Are there any ethical implications or any ethical problems connected with the cyclic model? Could that somehow influence also the practical?
Well, okay, so I'll give you an example of what I consider to be an ethical problem. According to the cyclic model, the basic motivation of it is to try to understand what happened at the Bang, and to make mathematical models. And so our statement, first statement, is that it's interesting to try to make a consistent mathematical model of the Big Bang itself. Now, some people don't even want to consider that. People say, no, this is beyond science. The start of the universe is not something we should be looking into. In fact, many ordinary people just say, look, you're getting into dangerous territory here. Explaining the Big Bang, that's religious territory. And so first of all, I'd like to say that it is an ethical statement, in my view, to say no, a subject like this is legitimate science. Not only can we do mathematics, we can do experimental tests, observations, and we should. And it's a wonderful and inspiring thing for people to think about. So I think it leads to a better appreciation of the universe. Even if you've got a model which is wrong, you're trying to understand the world. And in that process you appreciate it much better. But the second thing is again relating to this pessimism. Some people are arguing, even within physics, that we've reached the end of the road, and that there are some problems too hard for us to understand. And I think for me that's also an ethical question comes into it there. Because I think it's our ethical responsibility to keep going and to encourage young people who may have better ideas than we do, and not to say science, has maybe reached the end of the road. And so me, it's actually a very deep belief that if you like, even if science is going to be much more difficult from now on, it's something which we have to do. It's something which we cannot avoid, which our children or future young people will never forgive us for giving up at this point. So I feel very deeply about this, that I guess people talk about the golden age of various subjects, and people say maybe physics has had its golden age, and the next one is biology, and the next one is, maybe people should concentrate on engineering or something now. And I feel very deeply that's not correct, because I think what we have learned from physics is that nature is remarkably simple once you see through all the details. And it's one of the treasures of humanity that we have this picture, a very simple picture of nature. And I think if all we do is to take care of that picture and appreciate it, and by trying to generalize it, we actually help people learn it. And even if we ourselves don't succeed in taking the next step, at least we will have kept the whole subject alive and interesting. So yeah, I care very strongly about this, and I think the interest in this kind of pure science and pure thinking about the universe, and honest thinking about it. You know, we have to be humble. We're making models. They're probably wrong. we should take delight when we've proven them wrong and go forth with more energy and make better models. That activity, I think, is something which is common to all of humanity. When I meet students from Ethiopia or Madagascar or wherever, they are all fascinated with these things. And whatever culture people come from, they share it. So I regard physics as being very lucky to have this tradition and this set of knowledge which needs to be cultivated and worked on. And if the next leap takes 10,000 years, fine, we'll wait, because it'll be worth it.
But do you see any possible negative consequences? Like, could that knowledge that if psychic model proves to be right, would that knowledge be somehow, is it possible to abuse it in some way? Would it be?
Very likely. I think all knowledge can be abused. And it never comes with a stamp saying safe, safe knowledge. There is no such thing as safe knowledge, I don't think. And it's up to people to use it wisely. So I don't think there are any intrinsic ethics in science. I think ethics is something one has to add to science and try and use it sensibly. Having said that, I think I'm not worried about any applications at the moment. It's rather, it's very far in the future where people may be able to manipulate things at these energies. At the moment, laboratory energies we can reach are about 10 to the power 15 times too small to probe any of the physics of the bang itself. If we could build an accelerator that was 10 to the power 15 more powerful, then we could actually do this in the lab. That's a long way off. I think probably our descendants will figure out how to do it one day. There's nothing that prohibits it, but I'm not too worried about it.
Okay. So maybe now we can proceed with African Institute.
Well, there'll be two things. One, that's just finishing this theoretical bit. You said that in the last 2 months you've been developing some new ideas, which we will hold back on until you want us to let the world know. But what
no, they're already on the internet.
And you're going to try these out in various places in America and elsewhere. What are these? Can you summarize these?
Yes, I can. So probably the single greatest breakthrough of the last 10 years has been the realization that gravity is describable in a way without using gravity. So, as I explained earlier, gravity involves the deformation of space. It's the curving of space. And that's always been our picture since Einstein. But in the late 90s, a young Argentinian physicist called Juan Maltesina made a conjecture which is extremely interesting and exciting, and for which there's now a huge amount of evidence that it's correct. The conjecture was that in certain situations you can take a chunk of space which is dynamical, so the space can warp and bend, and that's gravity. You take this chunk of space, but the space is bounded by essentially a container. I mean, there's a boundary of space. And on that boundary, you have some matter moving and interacting with itself. But the boundary itself is not dynamical, it can't change. There's no gravity on the boundary. It's literally like having, if you like, a rigid cylinder, but with rubber inside. So it's flexible inside, but rigid on the boundary. Now his conjecture was that you could describe everything that happened in the interior purely in terms of what was on the boundary. It's called a holographic principle. Holography, as you know, is when you map a three-dimensional object into a two-dimensional picture. And that was his picture, that the interior would be mapped onto a rigid exterior, and then you could use a description, formulate a description of the world entirely in terms of what happened on the rigid boundary. And so this is very exciting, and it has been used to understand black holes, for example, when black holes evaporate and release their energy, how that process occurs, and how the information trapped in black holes emerges when they evaporate. But in the last few months, we've been using this to understand cosmology. So what we do is we map a dynamical universe, which is called the bulk. It's the interior, the sort of dynamical part of space-time. We map that onto a boundary, and we follow the system as it goes towards the Big Bang, or Big Crunch. So it heads to a singularity, and then we see what happens on the boundary, the singularity. And what we've shown is that on the boundary, you can describe exactly how the system goes through the singularity. And once you've gone through, so essentially you take the bulk which has gravity in it, you map it onto this rigid boundary, you follow it till it hits the singularity, you follow it through the singularity, you come out on the other side and you map it back into the bulk, where it's again described by gravity. And so we've constructed the first complete model of passage through a singularity. And it's very fascinating. Not only, it appears, can the world go through a singularity and survive, which is again, and this is another picture of the brain collision, in fact. The two things are related. So not only can that happen, but also in the process of heading towards the singularity, it turns out that variations in the density of the stuff on the boundary are created. And these variations in density from place to place are of exactly the form we need to explain the variations in density in the real universe. They're called scale invariant. And so the variations we see, which gave rise to galaxies, are known as scale invariant, meaning they're the same on all scales. And scale invariance is a very simple property. It's also a reflection of an underlying symmetry. And what happened is that Malvicina's picture, whereby gravity maps to matter in the bulk, on the boundary, that picture, the boundary theory, is automatically scale invariant. And so that scale invariance of the theory translates into the scale invariance of the density variations. So we've written a couple of papers about this, and there are many aspects still to be completed in the picture, but we think we have the means to do that. And if this is correct, if this picture turns out to be correct, it will be easily the most elegant explanation of the origin of the density variations, because it really all comes from symmetry principles, from gravity and from symmetry principles. So this is very exciting, and I'm presenting this work at several talks in the near future, and we'll see what the response is.
Lovely. I've got three more questions, if you can bear it.
Yeah.
One is, you've worked with a number of Cambridge cosmologists, and two I'm particularly interested in, that is Martin Rees.
Yes.
And Stephen Hawking.
Yes.
Martin talked about Stephen, who was
Right.
just slightly older than him.
Right.
How can you, as they say, compare and contrast those two
They are polar opposites.
Mm.
Martin's great strength is in keeping abreast of the latest observational discoveries and the latest facts about the universe, and trying to piece them together in a coherent picture. And so Martin's contributions, I think, to cosmology have all been what I would say on the phenomenological side. He looks at the phenomena and tries to make a sensible model of the phenomena. Stephen's contributions have been the opposite. Stephen has been interested in fundamental theory, meaning that from his point of view, mathematical consistency and elegance is primary. It's in the tradition of Einstein. Einstein essentially wasn't too worried about data.
You know one of his quotations?
No.
He said, if the data contradicts the theory, change the data.
So, he probably didn't mean that literally. But Stephen's work has always tried to employ the most advanced mathematical techniques to address theoretical puzzles and problems, paradoxes. So he would be much more interested in a sort of fundamental theoretical paradox than he would in the very latest observation. Having said that, Stephen has huge respect for the observations and interest in them. And should they become definitive, he might even believe them. But he doesn't really want to be, there's also a cultural difference between astrophysicists and theoretical physicists, by which I mean people studying particle physics, general relativity, fundamental theory. The cultural difference is that astrophysicists are usually very, very quick to jump on a new measurement. Every week there's a new type of star or galaxy or something detected, and astrophysicists will immediately want to say, imagine, what is that? And is the cloud of gas falling in, or is some dark matter swirling? Exactly what's happening. Theoretical physicists take a longer-term view of the world. It's not necessarily the right view. I mean, discoveries can be made in a moment, but there's just a different culture.
That's
and
lovely.
Martin and Stephen represent those two cultures.
That's very, very helpful. The second thing is, you talked earlier about your dissatisfaction with Cambridge, but here you are, a professor of theoretical physics or whatever. You're back. Is it a good place to work?
Cambridge has been fantastic for me, personally, mainly because two things. One is the wonderful collegiate atmosphere. I was working in Princeton before I came here, which is an excellent department, possibly the best physics department in the world, but much more, I would say, sort of aggressive and self-promoting culture. What's so enjoyable about it is that colleagues are very willing to spend time to discuss or to share ideas or their knowledge or their expertise without any agenda. I mean, just for the sake of it. And so that it has that culture which is excellent. The second thing which is great about Cambridge is the flexibility of the institution, that providing you fulfill a certain number of basic duties, which are pretty modest compared to other universities, you can do what you want. So for example, in coming to Cambridge, I had freedom to set up an institute in Cape Town and to raise money for it, and to bring in all sorts of allies and partners. And I don't believe there would be any other university in the world where I would have had that freedom. So Cambridge provides an open space, I would say. It's not too controlled, it doesn't have too much direction, if that isn't taken badly, but it does provide an open space, which is very, very valuable.
Which college are you at now? You're back at Churchill?
I've resigned.
Resigned?
Yes.
So you're not at a college?
I'm not at a college. I was at Downing College. I was at Churchill, but then after I moved here, I resisted joining a college. I didn't have time. And then I joined Downing. I was a member of Downing for 3 years. They gave me a nice fellowship. But in the end, I decided I wasn't bringing anything to them. I mean, I hardly went there. And I think the college concept is in severe need of renewal. I think it's become stale, and it's no longer, at least some the colleges, I don't know many colleges, but the colleges which I do know, some of them are no longer, I would say, a kind of genuine community of scholars. They've become too established, too less ambitious, and too many dinners.
Don't mention that. I had my second one in the week tonight. You mentioned your freedom to set up an institute in South Africa.
Yeah.
I heard a story which you can tell me whether it's true or not, that when you came back, now quite well known, if not famous, to your home on one occasion, your parents said, "That's all very well, Neil. I'm sure you're doing some really great stuff theoretically.
Yes.
But we're going to lock you in your room until you have an idea of what you might do usefully for South Africa, and then we'll let you out again." And you spent, according to this story, quite a long time in there, and then you knocked on the door and said, "I have an idea."
It's not quite true. It has a grain of truth. I went there, in fact Herbert Huppert helped me go there. I wrote to Herbert and I said, my daughter is, I guess this would have been 5 years old. I'd like her to spend some time with her grandparents. Can I take a sabbatical and go to Cape Town? So she has 3 months with her grandparents. So he wrote back and he said, "You've got to come up with a better argument than that." So I said, "Oh well, okay. I'll go and discuss possible collaboration between the University of Cape Town and Cambridge. How about that?" So he said, "Fine, I'll approve that as chairman of the faculty board, and off we go." So I went to Cape Town, and my daughter went to the local school there, and I was working in a little flat on the ekpyrotic universe. It was very wonderful. I had complete peace and quiet, and it was just excellent. But talking to my parents, the real thing is that I went to the university in order to fulfill this requirement that I establish a link with Cambridge. And I said, "Well, what could I do?" And they said, "We need maths. We need maths. South Africa has a strategic problem. We don't have enough students coming through with high-level math skills. What can you do?" So we talked around it a little bit, and it very quickly emerged. There's the whole of Africa out there. There's got to be some good math students. Let's bring them all to South Africa, which is a nice place to come. Bring the best international lecturers in the world, and we'll create some mathematical stars. So it was just sort of obviously the right time to do it, because South Africa is seen by respected by everyone, seen as a model for the future. So I had the idea, after meeting with people at the University of Cape Town, I had the idea, well, we just need an African Institute for Mathematical Sciences, just like the Isaac Newton Institute for Mathematical Sciences, and AIMS sounds a lot better than I&I as well. So I told my father about this, and we chatted about it a bit. He said, "Sounds great, I'm not sure we need mathematics." He didn't really get that part of it, but he said, "Sounds fine." And then the next day there was a rugby match on the TV, And so I said, well, I'll come over to your house and watch rugby. He said, no, he said, that's okay, providing you spend an hour in my office and you produce one page on the African Institute of Mathematics, then you can watch rugby. So reluctantly I came over, and indeed I spent an hour and I typed out this plan for a Maths Institute, and I watched the rugby. Next thing I know, he's faxed this to all the people he knew in higher education in South Africa, and then I had to do it. Sheer embarrassment. So he really got the ball rolling in a number of ways. He made me do it. He then, when I'd come back from South Africa to Cambridge, he called me up and he said, there's a fantastic building on sale in Muizenberg. It's 50 yards from the beach. It's an 80-room hotel, Art Deco, built in the 1920s, magnificent building. And we have to buy it, and you have to set up this institute in this building. I said, wait a second, I haven't got any money, haven't got any supporters, this is all a dream, and he said, no, let's go ahead and get this hotel. And to cut a long story short, we bought the hotel for £65,000 for 80-bedroom hotel, using an inheritance me and my brothers had. So my brothers allowed me to use this to buy the hotel. And then I brought the three deans of science from the local universities to the hotel, and I brought them in. I said, this is where we're going to set up the best maths institute in Africa. And one of those deans got very excited about this. The other two were supportive, but one was really enthusiastic. And he's now the director of the institute. And so we converted this hotel. And through a lot of hard work and good luck, it has indeed become a most amazing institute.
What a lovely story.
Yeah.
Thank you. Was there anything else you wanted?
Yes, I wanted to ask, just if I can just have two more questions about AIMS. I just figured out what a wonderful name it is, AIMS. When you said it.
Right.
How is it doing now? What are the results of...
Well, AIMS is in its fifth year. We've had 4 graduations. We've graduated about 160 students so far. They come from everywhere in Africa. So currently there are 53 students from 20 countries, including 20 women. And we designed it so to really be innovative. It has a very interesting program, which is quite unlike normal postgraduate programs in universities. It's all geared towards problem solving and encouraging people to think for themselves and take initiatives and so on. So it's been sort of designed with that in mind. And the students have been incredibly successful. Last year, I forget the precise numbers, but we had about 48 graduates, and 45 of them are now on master's and PhD programs in top institutions. One is a lecturer, one is doing an MBA, the other one's working in an IT company. These students are the most highly motivated individuals I've ever come across. And given 9 months at AIMS, which they use to the maximum, I mean, they work 16 hours a day, they learn computing and modeling, learn how to write, how to give presentations. They take full advantage of it. And they become very successful. And so I think we sort of stumbled on, through necessity and through not having enough money, we stumbled on a model of education which is extremely effective, which is you get a bunch of people from many different backgrounds, countries, cultures, but with common intelligence. They are all very intelligent people. And you bring them together and you recruit the best teachers in the world who are all willing to come to teach the best students in Africa. I mean, everyone's interested in Africa. They all say yes. And they all live in this hotel. And so it is a 24-hour learning environment where people will be up until 2 a.m. every night having impromptu discussions, tutorials, and so on. So it's a terrifically intense atmosphere. And after 9 months of that, these students are ready to go into anything. They can go into any field of science because they have all the skills that are needed. You see, this is what happens in an old institution like Cambridge. It develops layers of bureaucracy and rules and pro forma, curricula, which are almost fixed in stone. Whereas a new institution, can really jump to the cutting edge very quickly. And for me, there's a sort of purity about what's done at Ames, which is very exciting. That you think, what do we actually want to do? You're constantly thinking, what do we want to do? What's the most exciting thing? You have almost total freedom to do that. And the goal is very simple. It's to create, able people who can go into any technical field and contribute to it. The other thing is that by doing it in Africa, you automatically get students with very high motivation levels, because this is the chance of a lifetime for them. So that itself creates a unique atmosphere. So I think even though you might have thought Africa would be the last place you would develop the best model of postgraduate education in the world. In fact, it's been the best place to do it, because you're taking students who are so keen. See, for African students you come out of the Congo, right? They are just as ambitious as we are. They want to be the next Einstein. Everyone wants that. But they've just had tantalizing tastes of it. And often quite good maths education at school. There are surprisingly good maths lecturers in the Congo. So these students come out, and suddenly they're jumped to the cutting edge of science with the best lecturers. And boy, are they excited. And creative. They want to do things. We had a wonderful guy in the first year who arrived from the Congo, and he arrives, he says, what do you want to work on? He says, well, I'm interested in quantum mechanics, I'm also interested in chaos, so I think I'm going to do quantum chaos. Okay, so he didn't know what it meant, of course. But he took a course on information theory at Ames, he took a course on quantum mechanics, and he wrote his essay using very sophisticated information theory to understand quantum chaotic systems. And this was actually innovative at the time. And this guy as well, he writes poetry, he won a cookery prize in the International Students Association, he spent his time in schools teaching kids. He's just a sort of Renaissance man, and he's an African. And that's the kind of students who we are finding. And so my conception of Ames went from its being a sort of necessary step to solving a strategic problem, which is the lack of highly skilled people in Africa, more towards the conception that actually this will benefit science in the long run. Because I believe that when these cultures and people from different backgrounds and cultures come into science, they all bring a new energy and freshness, enthusiasm, and very likely some new ways of looking at things. And so I think this is a huge benefit to science. I mean, this year we have 5 students from Ames in the maths department. Previous to this, you would essentially never see a black African in maths department. And the ones you saw were very isolated and felt second-rate and alone. This year we've got 5, and it's just the beginning. These students are on top of the world, and they're having a fantastic time. and I'm actually hopeful that one of them will come at or near the top in the financial maths course here. Very brilliant student. And we've now set out, is our culture attains, that we're going to prove something to the world, which is that black Africans are every bit as good at science as whites. And now it's become a matter of principle. For example, you know, there was this ridiculous statement by Jim Watson.
Yes.
I don't know if you heard what happened subsequently. His genome was sequenced and shown to be 16%
Yes, that's
African.
right.
But we sort of use this story to egg the students on, and they really take it on board. And one of our sort of dreams at Ames, which we repeat and which I will say at this TED meeting, is that our dream is that the next Einstein will be in Africa. And the students love that. It's about self-respect. It's about seeing, you know, the opportunities in Africa, not just all the problems, huge problems. But I think the world, you know, needs to change the way it looks at it. We don't want charity. We want, you know, dynamism and energy. And Africa has so much to offer the world. So that's really the philosophy of the SAMES project. Yeah.
You mentioned TED conference, so my last question would be that winning the TED prize means winning $100,000, but more importantly, you're granted a wish. Can you tell us what your wish will be, or is it
providing you don't publicize it before next Friday?
No, I won't. No possibility.
So the wish has two parts. The first is the dream. The dream is the next Einstein will be an African. And this dream may sound surprising or shocking. I mean, how could there be another Einstein? And how could it possibly be an African? But if you think about it, it's not really that shocking. Einstein was a Jew, and Jews didn't really get into science until around 1880. They were actually prohibited from going into universities in many countries in Europe in the 19th century. Some Jews went into medicine, very few went into hard science. But once they got into it, starting in the late 1880s, Hertz and Jacobi were the famous sort of physicists, mathematicians, then Einstein, Pauli, and then, you know, Born, huge numbers of them. And so that over 1/4 of all Nobel Prizes in physics have been won by Jews, and 1/4 of the Fields medals in mathematics have been won by Jews. So is that something innate to Jews? You know, I don't believe so. I think, yes, there's some elements of Jewish culture which are helpful. A great respect for the written word, for study, you know, which goes back to biblical times. But I think more important than that is that they were out to prove something. I mean, that the Jews were a suppressed group of people, had suffered horrendous, you know, discrimination and oppression. And when they got half a chance, they wanted to prove something about themselves. Now look at Africa. Culturally, possibly, you know, one of the richest continents on the planet. I mean, half of our music comes from Africa. Art, design. I mean, anyone who tells me Africans don't have logical minds, you know, has never seen a bush mechanic in Africa fix a 50-year-old car, right? Or steam engines. There's still steamboats working in Africa. Why? Because they're incredibly clever, ingenious mechanics. I've seen a guy fix a radio, a valve radio, used at the mission school, which I taught at in Lesotho. Completely untrained, but he kept that working, and he understood it in some way. I don't understand it, but he understood it. There is genius all over Africa. I'm convinced of that. I've met some very bright kids. I must tell you one story. When I was teaching in...
We've got 2 minutes.
I was teaching,
for the wish as well.
Oh,
Okay.
for the wish. I was teaching in Lesotho, and I took the kids outside for to try to connect mathematics to the real world. And I said to them, okay, estimate the height of this building. And I thought they'd put a ruler and sort of, 5 meters, something like that. So there's a little kid and he's drawing on paving stones with chalk. I thought, he's completely misunderstood. What are you doing, get the height of the building? He said, yeah, I'm doing the height of the building. He said, I measured the height of a brick and I counted the number and I'm multiplying them and that's the height of the building. Well, that beat me. So I think genius is everywhere, and that's the first part. The next act's on in action. The second part of the dream is a plan. We have a very concrete plan to replicate AIMS all over Africa. Mm-hmm. We're trying to get major sponsors on board. There are indications that Bob Geldof will support it. Mm. I'm having a conference call with PricewaterhouseCoopers on Friday to try to get them to be the auditors of this project so that the finances are kind of 100% sorted out, management, training skills, all of this. We want to do this properly. And at TED, this is what I'll be asking for. So we're looking for 3 corporate donors who will give all private donors who will give $50 million each, and that will set up an endowment fund which will fund student scholarships at AIMS and AIMS partner institutes all over Africa. And then we'll go to governments. We already have the support of the African Union. They've already commissioned us to prepare this plan. And so we have political support all over Africa. We have partners all over Africa. We have sites in Nigeria, Ghana, Uganda, Sudan, Madagascar, which we've visited. We have business plans. We're getting organized, and we want to do this properly. And I think when it's done, we'll have a network of AIMS, and we'll be producing about. We hope to have 15 centres after 5 years, each one producing 50 graduates per year. And those graduates will all go, some in actually academia, some into government, industry, entrepreneurs, and we think they could have a major impact in African development. So that's the future of AIMS.